So we also need to, update stuff. So do we allocate cache lines on a write? So say I want to write some variable, but I don't see it in my cache. Then I need to bring it into the cache. There's another strategy that does not do that, but let's focus on this one. So you bring that into the cache. Do we update the memory on write? So for example, write back strategy would mean that the memory is updated, so the cache is updated when the line is replaced. So I update it, and I actually update that block, the data block in that cache line. So now I'm not talking about a hierarchy of caches, but if you have like an L1 cache and an L2 cache and so forth, then clearly you have an eviction strategy between the L1 and the L2 cache and the L2 and the DRAM. So how would you like to structure that, for example? So that we haven't talked about, and I will just glance over it in a minute. But I just want to make sure that you understand there's a bunch of stuff that you may need to think about when you do caches. So let's focus on the write back cache. So now we need an extra bit for each line. So if I read something from memory, then I need to remember whether I updated it to a new value or not, because if I did not, I don't have to access DRAM on a eviction because it was not updated in the first place. So nothing is changing in the DRAM, so I don't have to incur that latency. So I need an extra bit in addition for that cache line that indicates whether I've changed it, whether I've updated it to something new. So that's what we call the dirty bit. So the line starts as a clean state when you get it in, and when you update it, when you write to it, you make it dirty. And when you need to evict a dirty line, then you really need to ship it out to memory. So that you would like to remember as well. So then we have prefetching. That's a very different thing. We talked a little bit about. No, we may not have talked about prefetching, but anyway, it's a good thing to do prefetching. You could look ahead, right? Like you have some understanding of your program behavior to some extent, and you look ahead in say the instructions that you will be dealing with, and you may be to some extent minimize future misses by doing proper prefetching. You don't need it right now, but you prefetch it for the future. So it's a separate buffer that you can have. So prefetch buffers. So then there are more advanced topics that we're not going to talk about, but you can have inclusive and exclusive caches in such a cache hierarchy where, effectively, say the L1 cache is included, all the information there is included in the L2 cache. That's one strategy, that's inclusive. Exclusive is the other way around. And it requires different kinds of updating, and has different pros and cons. You have blocking and non-blocking caches. If you have a multi-core, you may want to fetch a data element, but you're not going to block it, actually. So until you actually get it, and so forth. So there's these types of trade-offs, and then you need to, of course, make sure that everything is is agreed upon between all those different threads, and so forth, and these cores, and so forth. So this is the slide deck on caching. It's just meant for you to get a little bit more of a feeling for this whole topic, because after all, you're writing a lab 2 and implementing a cache policy. You just have one cache, right? A lowest level cache, so no cache hierarchy, and there you will actually implement such a caching algorithm. And then what you want to do, you want to measure the performance penalty that you see, right? So you want to understand, you want to simulate, you want to emulate that behavior. Now, The next lab after this, you will implement a new hardware module, which is a memory integrity checking mechanism. That's pretty cool. So now you want to understand how caching helps, or with that, or not helps. We will talk about it on next lecture. And you want to demonstrate that in your emulation tool. And then after that, we will have a lab in which you want to create your own covered cache channel attack. So you will need to show an example in your emulator. You create your own benchmark effectively, 2 benchmarks that are executing, and you show that you can leak information from one to the other. And then you will need to implement essentially Sanctum's ID. The hardware implementation is much more difficult than just the simple algorithmic interpretation of it, but so that's what you will probably implement, and you will then see that that avoids you to learn anything from like that process, that you will not have a side channel. So that's what we like you to struggle with. And I actually think maybe the first lab 2 is maybe the hardest to do, because you need to get yourself familiarized with all the tools. But I think lab 3 and lab 4 would be an easy breeze after that. And then we have 2 more labs after that. Okay, so that was that. So now let's start our review part. And to do so, we are going to talk about this, the extra slides. I will start talking about this first, because I got a few questions after the Monday lecture, and I thought maybe this will help a lot. It's a lot of text, I could not clean that up in nice pictures and all that. But I first want to recap that we're talking about isolation and attestation. So in the first part of the lectures, what did we really do? We started to look at how an STX enclave, what its structure is. How is it isolated from all the rest? So, yeah, you create an enclave and you manage a secure enclave and so forth. So we analyzed in detail into what extent computation that takes place in a secure enclave is vulnerable to privacy leakage effectively. So we talked about that you really want to isolate the data and instructions that you use in the enclave from being accessed by anything else, other enclaves, or untrusted OS. So we have a bunch of checks. Remember one of the first lectures? A bunch of checks in place where we use this EPCM register, I believe, to figure out whether entries are valid or not. Like, are they used already in that reserved memory, so that we will not conflict if we start a new enclave and we need to store it and we don't give it access to what was already there, and there are some other tags in there that you need to use to do proper checking. So, for example, that's one part, that is hardware isolation. But in addition, and this will be talked about next lecture, so after the quiz, is the management encryption engine that implements with basic crypto primitives, encryption and memory integrity checking. So what maybe the conclusion is that if we have a secure enclave, we can really protect leakage. Now, we showed that there are a bunch of vulnerabilities still, right? That we had discussed, but effectively, outside that range of vulnerabilities, there seems to be no privacy leakage. So the beautiful thing is, the conclusion I would say is that we use hardware with what hardware is good in, which is hardware isolation, and that brings security. And we use crypto with what crypto is good at, which is simple encryption, simple hash functions and stuff like that, that have been well studied and demonstrated to lead to believable trust assumptions, like computational hardness assumptions that we think are really hard. Now, we have been discussing this kind of environment, right? And you want to, of course, understand what that environment does for you, into what extent is it isolated and what extent is it not. But let's assume we now have that secure sort of container. That's not enough, right? If I want to compute something in a secure container, and I'm a remote client who does that, how do I know that it has been executed in that secure container and is not executing somewhere else, where potentially someone else, an attacker, could have looked into it simply because it's not a secure container, so privacy leak is all about, and I have a problem. So I want to verify, that is, attest, that the output that I receive back as a client from such a secure enclave is actually the right output. In other words, it's authentic. It comes from that particular enclave. That means a couple of things, right? It means it comes from an enclave with that particular identity. It even comes from that particular processor. And I may even want to know a little bit more information. I may want to know maybe how that enclave corresponds to maybe an owner signature that I also trust, because the owner has been creating these types of enclaves, or the author of the enclave is known to do a really good job to make sure that the application code itself does not have vulnerabilities, for example, or not many at least, or has done a good job on that. So what we see here is that we have that, and we also need to make sure it's fresh. I mean, you can of course always send you an older version of what was computed in that particular enclave, but I also need to make sure it's the most recent one, or the one that I'm interested in. Yeah.